There exists a moment each morning when the world is still held in darkness, yet somewhere below the horizon, light is already beginning its ancient journey toward you. For thousands of years, humans have watched this same threshold, this turning point where night yields to the possibility of day. But what if I told you that the warmth now spreading across your face, the golden glow that reaches your eyes through the window, is not born in this moment at all, that it is, in fact, older than your entire existence, and that its creation took place 8 minutes and 20 seconds before it touched your skin? The sun, that patient star hanging above us, is constantly sending us light that began its voyage long before we were even aware it was coming. It is perhaps one of the most profound and gentle truths of our existence, and one that changes the way we experience even the simplest dawn. If these quiet wonders of our solar system speak to you, if you find yourself drawn to the hidden stories of the cosmos told in hushed tones and measured breaths, consider subscribing for more calm journeys through the peaceful science behind the most relaxing facts about sun. These explorations unfold slowly, designed to guide your mind toward rest, while revealing the serene truths that have always surrounded us. And so we begin in that tender hour before full light arrives. Picture, if you will, the horizon line where Earth meets sky. The darkness above is still profound, still complete, yet along that thin border where the curve of the world catches the sun's rays at a shallow angle, something extraordinary is beginning. A faint warmth appears first, a sensation before a vision. Then, almost imperceptibly, a blush of color begins to stain the edge of the night. Soft violet, then pink, then a deepening rose that seems to emanate from within the sky itself, rather than shine upon it from without. The light moves slowly, with no hurry, no urgency. There is no violence in it. It does not burst forth or explode into being. It creeps, it spreads, it gradually and gently dissolves the darkness, like a mist thinning before a slow breeze. As this light climbs higher, the colors shift and deepen. The violet deepens toward blue, the pink becomes gold, the gold becomes amber, and all the while, the stars that filled the sky mere moments before begin to fade. Not dramatically, but like a memory that softens with time. They do not disappear, they simply recede, becoming invisible not because they have gone away, but because the growing light renders them unnecessary to our vision. The sky itself seems to breathe during these moments. It expands with color, it exhales warmth, and if you were standing still in that twilight, feeling the temperature of the air shift from cool to tepid, you would begin to sense something profound, that this light, this warmth, has traveled vast distances to reach you. It has journeyed through the vacuum of space itself, and it carries with it a story of unimaginable duration. The horizon brightens further. Where it meets the land or sea, a sharp golden line forms, a demarcation between the night that is ending and the day that is arriving. This line is the first direct sight of the sun itself, still hidden beneath the curve of the earth. The sun has not yet broken free from the world's edge, yet already its light dominates the sky above. Already it has transformed everything. The clouds, if there are any, become gilded. Their undersides glow with an inner luminescence as if they themselves are sources of light rather than merely recipients of it. The world below, trees, buildings, water, grass, begins to take on definition. Shadows, which during darkness were indistinguishable from the rest of the night, now have clear edges. They lie long and dark upon the ground, cast by the sun's approach from the far side of the world. These shadows are among the most peaceful sights dawn offers. They are not threatening, they are calm, they are simply places where the light has not yet arrived, and they remind us that the world has dimension, has depth, has substance. Then comes the moment when the sun's upper edge finally breaks through the horizon line itself. Just a sliver appears at first, a crescent of brilliant white-gold light that is almost too bright to look at directly, even from this distance. This moment has been anticipated by every living thing on this side of the planet. Plants orient themselves toward it. Animals that have been still through the night begin to move. The light, now that it comes directly from the sun itself, rather than reflected through the atmosphere, carries a different quality. It is warmer, it is more assertive, yet still, it rises slowly. There is no rushing. The sun does not leap from the horizon. It climbs with patient inevitability, each moment bringing it slightly higher into the sky. As the sun rises further, more of its face emerges. The light spreads laterally across the horizon, illuminating everything in its path. The world that was hidden in darkness is revealed incrementally. Colors that were invisible hours before begin to emerge. The green of grass becomes visible. The blue of water deepens. The texture of bark on trees becomes apparent. The details of distant mountains or buildings become clear. It is as if the sun is not only providing light, but is actively discovering the world, moment by moment, revealing it in layers. And what is remarkable is how completely it does this without force, without disruption to the still morning air. The light simply arrives, and the world simply responds. The warmth intensifies on your skin. If you were standing outside in this dawn light, you would feel the temperature rising gradually, almost imperceptibly, as each new portion of the sun emerges above the horizon. This warmth is not the heat of fire or the blast of an oven. It is gentle, inviting, almost like an embrace that the sun extends across the great distances between its surface and ours. There is something profoundly comforting in this warmth, something that reaches not just the outer layer of skin, but seems to penetrate deeper, to touch something in us that responds to light at the most fundamental level. There exists a peculiar and rather wonderful truth about the light touching your skin in this very moment, a truth that dissolves the boundary between now and then, between you and the vast furnace overhead. The warmth you feel, that gentle golden pressure on your shoulders or your face or your hands, it is not arriving fresh from the sun. It is 8 minutes and 20 seconds old. 8 minutes and 20 seconds. Let that settle for a moment. The photons that crossed your eyelids this morning were born in a place you will never visit, in a region of such density and heat that matter itself transforms into pure light and energy. And then they traveled across the void of space at the fastest speed anything can travel, and still they took more than 8 minutes to reach you. Which means that the sun you see, if you were to look at it right now, is not the sun as it is. It is a portrait of the sun as it was, a ghost image, a memory inscribed in light. Consider what happens in those 8 minutes and 20 seconds while the photons journey toward Earth. The sun continues its quiet work. Hydrogen fuses into helium in its core. The solar winds ripple outward. The magnetic field shifts and trembles. The planets wheel in their orbits. You draw breath. And somewhere far below the sun's visible surface, in depths that no instrument can truly penetrate, new light is being born constantly, endlessly, a tide of energy that will take thousands of years to reach the surface, but which will eventually, patiently, make its way outward and then downward through the cosmos toward waiting worlds. The sunlight warming your skin tonight connects you backward through time to the sun's hidden interior, a chain of cause and effect stretching back through the vacuum between worlds. This delay, this gentle lag in light's arrival, is not something to lament. It is something to marvel at. It tells us that we are always, in a sense, looking into the past whenever we look toward the sun, and yet the warmth we feel is utterly present, utterly now. There is a meditation in that paradox. The light left the sun 8 minutes and 20 seconds ago, but it arrives to you in this exact moment of your listening, in this exact breath, when the world is quiet and stillness surrounds you. So in a way, the sun's light is both ancient and immediate, both a memory and a present gift. It carries within it the story of the sun's depths, of the nuclear reactions that have been burning in that stellar furnace for billions of years, that will burn for billions more, indifferent to our small Earth, yet giving us life nonetheless. The sun we know through our senses, through warmth and light and color and shadow, is thus a subtle collaboration between the physics of the distant star and the geometry of space itself. The time it takes light to cross that gulf is not an accident or an obstacle. It is a feature of the universe as fundamental as gravity or the speed of light itself. And somewhere in the mathematics of that 8-minute and 20-second journey, there is something beautiful. It means that the sun is always partly mysterious to us. It means we can never quite possess the present moment of the sun, only its near past. It means we are always reaching towards something that has already moved beyond the image we hold in our minds. This is perhaps one of reason's most humbling gifts. Not that we now understand sunlight travels at a finite speed, but that we can hold this knowledge gently in our awareness and feel, at the same time, the sun's warmth on our skin as something real and close and intimately ours. The journey of those photons born in nuclear fire and traveling across the vast dark ends in your skin, in the gentle heating of your body, in the stimulus that tells your nervous system that the day is here, or the memory of the day still lingers. That journey connects you to a process that began 5 billion years ago, in a collapsing cloud of gas and dust, before you existed, before the Earth existed, in a time so distant it exists only in mathematics and the patient work of cosmologists and physicists who study light and ask it questions about its origins. Yet here is that light, arriving to you, always just slightly late, always carrying within it the whisper of a star's deep interior, always reminding you that you are made of the same elements that burn in the sun's core, that you are connected to that great furnace by threads of light and time and ancient chemistry. There is a certain quietness to knowing this, a certain peace in understanding that the sun is not merely a distant object in the sky, but a presence that reaches into the very depths of your being, warming the skin at the cellular level, influencing the rhythms of sleep and wakefulness that govern your nights and days. The sun has been doing this, patiently and without complaint, for billions of years, and it will continue to do so for billions more. If you find yourself drawn to these gentle explorations of our solar star, to the quiet wonders hidden within its layers, to the invisible winds it sends streaming across the planets, to the distant future it will one day reshape, then consider following this journey further with us. We are creating a series of calm passages through the most serene facts about the sun and the cosmos it inhabits. Each episode unfolds slowly, the way truth itself seems to reveal itself in the darkness before sleep takes hold. There is no rush, no urgency, only the patient unfolding of how a star works, how it breathes, how it has shaped every living thing on this small blue world we call home. Subscribe now, and let us guide you through the luminous quiet of solar science, through the mysteries of its birth, the secrets held within its core, the ways it speaks to Earth through light and wind and shadow. These are the stories that wait for you in the stillness of evening, the kind of knowledge that settles into consciousness like a gentle tide, carrying you toward deeper rest. For now, though, let us continue our descent into time. Let us journey backward, beyond the reach of that 8-minute-old light, beyond even the age of human civilization or the formation of Earth itself. We must travel almost 5 billion years into the past, to a moment when nothing existed here but an enormous cloud of gas and dust, slowly beginning its own slow conversation with gravity and the long, patient process of becoming a star. And so we turn our attention backward now, backward through incomprehensible time, following the thread of light and matter to its source. Nearly 5 billion years ago, before the sun existed, before Earth orbited it, before anything we know had taken shape, there was a cloud, vast and cold and patient, It drifted in the darkness of space, a nebula composed almost entirely of hydrogen and helium, the two simplest elements in the universe, scattered through with trace amounts of heavier elements, carbon and oxygen, silicon and iron, the dust of older stars that had once burned and then released their matter back into the cosmos. This cloud had no name, no observer. It simply was, turning slowly in the galactic arms, indifferent to its own existence. But something was stirring in the quiet. Deep within the nebula's expanse, gravity, that patient, tireless force that shapes everything, was at work. It would be easy to imagine gravity as something dramatic, violent, an aggressive pulling force. But it was none of those things. It was something far more subtle. Gravity is the gentlest of the fundamental forces, so weak that you cannot feel the gravitational pull of even a mountain standing beside you. Yet it is also the most patient. Given enough time, it wins everything. Within this vast cloud, in regions where the gas happened to be slightly denser, gravity began to accumulate. Particles were drawn toward particles. Dust grains clustered around dust grains. The process was unimaginably slow at first. What felt like stillness, like nothing at all. Molecules drifted closer together, atom by atom, over thousands of years. But once the process began, once the density in one region became just slightly greater than in another, gravity fed upon itself. The greater the concentration of matter, the stronger the gravitational pull became. The stronger the pull, the more matter it drew inward, and so the cloud began to collapse. Picture it, if you can, a region perhaps as wide as several light years across, slowly compressing inward. The compression was not uniform. Parts of the collapsing cloud fragmented, broke apart, formed their own collapsing centers. Some of these fragments would eventually become stars. Others would become planets, asteroids, the scattered remnants we see today. But one of these fragments, one particular knot of collapsing matter, was destined to become our sun. As the collapse continued, as more and more material fell inward, gravity's work deepened. The cloud that had been cold was beginning to warm. When you compress a gas, when you squeeze it into a smaller and smaller space, its temperature rises. This is not magic, but simple thermodynamics, the physics of how matter behaves under pressure. The collapsing sun-to-be was squeezing itself. Gravity was pressing inward from all directions, and the gas at the center was beginning to heat. The rotation increased as well. Picture a figure skater drawing their arms inward, spinning faster and faster. The nebula's original, barely perceptible spin became increasingly pronounced as material fell inward. The collapsing cloud began to take on the shape of a disk, rotating faster and faster, flattened by the centrifugal effect, with most of the material concentrated toward the center. This rotating disk of infalling gas and dust would eventually become the solar system itself, the sun at the heart, planets and moons circling in the planes of that ancient rotation. For perhaps 100,000 years, or perhaps 1,000,000, timescales that even now seem almost unimaginable to the human mind, this process continued. The sun-to-be, sometimes called the solar nebula, grew denser and hotter. Material continued to fall inward. The central region, compressed under the weight of billions of kilometers of gas above it, reached temperatures of hundreds of thousands of degrees. And still, gravity continued its patient work, compressing and compressing, drawing more material toward the center, condensing what had been a vast, diffuse cloud into something increasingly concentrated, increasingly dense, and increasingly warm. The thing we must understand is that this was not a sudden event. There was no moment when gravity turned on, no instant when the sun sprang into being. Instead, there was a slow transformation. Matter that had drifted freely in space began to gather. A region of space that had been empty, or nearly empty, began to fill. A temperature that had been near absolute zero began to climb. The transition was gradual, almost gentle, as if the universe itself was patient enough to spend hundreds of thousands of years building something magnificent out of nothing but dust and gravity and time. And as the density increased, as the weight of all that falling material pressed downward, the temperature at the very center of the collapsing cloud reached a threshold. It climbed toward 5 million degrees, 10 million. And somewhere in that slow, inexorable climb, something shifted. Something fundamental was about to happen. The hydrogen atoms being squeezed in that furnace at the center were about to transform. They were about to begin fusing, and in that fusion would be born the first light of our star. And within that slow-turning cloud, suspended in the silent dark of space, something patient and invisible began its work. Gravity, that ancient force, gentler than a whisper, yet more patient than any living thing, started to draw the scattered particles inward, toward a center that did not yet exist. Imagine a cosmic dance so slow that it would take millions of years to detect any motion at all, yet every single atom of hydrogen and helium and dust was being pulled, ever so gently, toward the same invisible point. The cloud began to collapse upon itself, not in any violent rush, but in a graceful, inexorable contraction. At first, the particles fell inward only slowly, but as more material gathered toward the center, gravity's grip grew stronger. The cloud spiraled and flattened. The density at its heart increased, degree by imperceptible degree. And then, after untold eons of this patient compression, something remarkable happened. The pressure at the core became so immense, so overwhelming, that the temperature began to rise, not from any external heat, but from the simple, profound fact that matter crushed together generates warmth. It is as if the universe itself had been holding its breath, waiting. The center of that collapsing cloud grew hotter and hotter still. The particles moved faster and faster, colliding with increasing violence, their atoms stripped of their electrons, becoming something utterly transformed, plasma, pure energy given almost physical form. At some point in this slow crescendo of pressure and heat, at some moment that we can calculate but never truly witness, a threshold was crossed. The temperature at the sun's core reached approximately 10 million degrees, and at that temperature, something momentous and serene occurred simultaneously. The hydrogen nuclei at the very heart of all that gathered material began to fuse. Picture this, if you will. 2 hydrogen nuclei, the simplest atoms in the universe, were squeezed together with such force that their strong nuclear force overcame the electromagnetic repulsion that ordinarily keeps them apart. They merged. And in that fusion, they became something new, helium. And as they did, something astonishing happened. A tiny amount of mass vanished. It did not disappear. It transformed into pure energy, according to the equation that would one day be written by Einstein. The energy released by that single fusion reaction was almost incomprehensibly small, but it rippled outward, and then another fusion occurred, and another, and another. Within the core, a chain reaction began, millions upon millions of hydrogen nuclei fusing every single second, each one releasing a thread of energy. The core grew even hotter still. The pressure increased further, more fusions occurred. Faster, more intense, yet all of this was happening in perfect silence, in perfect stillness from the perspective of the cosmos. No explosions, no dramatic flare, simply the quiet ignition of stellar fire born from gravity's patient, invisible pressure. This was the moment the sun truly became the sun. Not a collapsing cloud, but a star, a furnace, an engine of unimaginable power held in equilibrium by the balance between 2 opposing forces. On one side, gravity pulling inward with constant patience. On the other, the outward pressure of all that nuclear fusion, all that heat and light and energy, pushing back with equal and opposite force. These two forces found their balance, and in that balance, something stable emerged. The sun settled into a state of equilibrium that would last, we believe, for billions of years. It would neither collapse further nor explode. It would simply burn. And as it burned, photons of light were created, packets of energy born in those nuclear furnaces deep within the stellar core. These photons would eventually find their way outward, through layers of churning plasma, through zones of radiative transport, through convection cells that would twist and turn like the slow breathing of some vast, sleeping creature. They would eventually emerge at the surface and travel across 93 million miles of empty space to reach your eyes, to warm your skin, to make possible every living thing that has ever existed on this small blue world. But all of that was still to come. At the moment of ignition, when gravity's patient squeeze finally sparked that first fusion reaction, the sun had simply become what it was always meant to be, not through force or hurry, but through the quiet, inevitable pressure of time and physics and the deep geometry of the universe itself. A star had been born, and with it, the story of our solar system had truly begun. Now imagine, if you will, stepping beyond the visible surface of the sun, past that glowing boundary where light finally breaks free, and descending slowly into a realm of absolute darkness and unimaginable pressure. This is the hidden heart of the sun, layered like the quiet depths of an ancient ocean, each stratum more strange and transformative than the last. We cannot see this world with any telescope or satellite, yet through mathematics and the patient observation of how the sun trembles and oscillates, scientists have mapped its invisible anatomy with remarkable precision. At the very center, compressed by the weight of 730 billion tons of solar material pressing inward, lies the core. Picture, if you can, a sphere roughly the size of Jupiter, already incomprehensibly vast by earthly standards, yet containing more than half of the sun's entire mass. Here, in this crucible of extremity, the temperature climbs to nearly 27 million degrees Fahrenheit. The pressure is so extreme that it achieves something physics ordinarily forbids. It forces atomic nuclei to fuse together. Hydrogen nuclei collide and merge, moment after moment, throughout each second, releasing the radiant energy that has sustained life on Earth since our planet was young. This is not an explosion, though it resembles one in description. It is, rather, a steady, eternal chain reaction of transformation. 4 hydrogen atoms become 1 helium atom, and in that simplification, mass converts to light. That light, that energy born from the marriage of nuclei, is the engine of all you have ever witnessed. Moving outward from this nuclear furnace, we enter the radiative zone. This layer extends roughly 40% of the way from the core to the sun's surface, and it is a realm of profound patience. The photons, the particles of light that were created in the core, do not simply flee outward in straight lines toward freedom. Instead, they collide constantly with the plasma surrounding them, bouncing and scattering and being reabsorbed in an almost dreamlike wandering. Each photon travels, on average, only a centimeter before encountering another particle and being redirected. Over thousands of years, over dozens of thousands of years, these light particles gradually work their way outward in what physicists call a random walk. Imagine a traveler in an endless fog, taking one blind step at a time, never quite knowing whether the next step carries them closer to their destination, yet over time, inching steadily forward. This is the profound journey that every particle of sunlight takes through the radiative zone, a slow, patient migration from the fury of creation toward the possibility of illuminating distant worlds. And then, passing through an invisible threshold, we arrive at the convective zone. Here, the sun's behavior transforms entirely. The temperature has cooled, relatively speaking, to below 2 million degrees, At these lower extremes, the plasma can no longer transport heat efficiently by radiation alone. Instead, the sun relies on convection. Imagine vast currents of superheated material rising upward like the slow breathing of something alive, carrying heat from the depths toward the surface, while cooler, denser material sinks back down to be reheated. These convective cells are enormous, each one thousands of kilometers across, and they churn and circulate in patterns that scientists are still working to fully understand. They move slowly, yet they are perpetually in motion, a gentle churning that fills the outer quarter of the sun's interior. What is most striking about these three zones is how they represent three distinct methods of moving heat and energy outward, each suited to the particular conditions of that layer. The core creates. The radiative zone transmits with infinite patience. The convective zone stirs and carries. Together, they form a system of such elegance and balance that the sun has maintained its steady glow for over 4 billion years. From the quantum dance of nuclear fusion in the core to the great turning currents of the convective zone, the sun is a machine of transformation operating on timescales both infinitesimally small and geologically vast. Each of these hidden layers is working silently, perpetually, reshaping the very atoms that compose them, converting one element into another in an endless alchemy. This is the secret architecture of the star that rises each morning, a hidden, orderly world of immense complexity, sealed forever behind a luminous veil. And so within this luminous engine, within those millions of degrees of pressure and heat, something remarkable unfolds, something that takes not seconds, not minutes, but thousands upon thousands of years to complete. A single photon, a particle of light born from the collision of hydrogen nuclei deep in the sun's core, begins a journey that is almost incomprehensibly slow and patient. Picture it, if you will, a moment of fusion, an instant when two particles collide and release their energy as a tiny spark of light. That photon, that smallest possible messenger of radiance, is now surrounded by an almost impenetrable ocean of other particles. The core of the sun is so densely packed, so crowded with matter, that a single photon cannot simply travel outward. It cannot take a straight path into open space. Instead, it tumbles through this dense medium like a pebble, sinking through a forest of trees, constantly colliding with electrons and ions, constantly being absorbed and re-emitted, moving in what we might imagine as a kind of cosmic shuffle, forward one infinitesimal step, then another again. The radiative zone that surrounds the core is nearly as opaque, nearly as crowded. For hundreds of thousands of years, this single photon bounces between particles, each collision sending it in a slightly different direction, each absorption and re-emission consuming time that we find difficult to truly comprehend. It takes, on average, somewhere between 170,000 and several 100,000 years for a photon to make its way from the core outward through this radiative layer alone. Some physicists suggest the journey might take even longer, depending on the precise path the photon takes, depending on the exact distribution of particles it encounters. Consider this for a moment. The sunlight that falls upon your face this very instant, the warmth you feel on your skin right now, was created before human beings walked upright on the African plains. That photon was born in the furnace of the sun during an epoch when the Earth's continents were configured in completely different arrangements, when the creatures that roamed our world bore no resemblance to anything alive today. And yet it is only now, after all those millennia, that it reaches you. The convective zone, that outermost region we explored, is slightly more merciful. Here the plasma flows more openly, the particles are somewhat less densely packed. But even so, a photon that has already traveled for 250,000 years must still navigate through layers of roiling, churning gas before it finally bursts free into the emptiness of space. Some portion of that journey through the sun's interior might take only thousands of years, but other photons, other tiny messengers, might take far longer still. There is a kind of gentle randomness to it, an acceptance that some will move swiftly and others will wander. This is perhaps one of the most soothing paradoxes of the sun, that from our perspective, that glowing disk appears constant, unchanging, perpetually present. And yet every photon we see, every quantum of light that reaches us, carries within it the patience of a journey spanning eons. The sun is not merely heating us in the moment, it is sending us light that was shaped during epochs we can barely fathom, light that took longer to escape the sun than human civilization has existed to witness it. When a photon finally emerges at the sun's surface, when it finally breaks free from the densely packed interior and enters the relative openness of space, it has been traveling at the speed of light for the latter portion of its journey, yes, but only for the latter portion. For the vast majority of its existence, it has been slowly, patiently working its way outward, absorbed and re-emitted countless times, transformed and retransformed, a single quantum of energy persisting through thousands of generations of the sun's internal activity. And what makes this even more remarkable is that the sun produces so many photons, such an incomprehensible abundance of them, that despite this staggering delay, despite the fact that light born today will take millennia to escape, the sun's surface is nevertheless brilliantly illuminated. The core is continuously generating new photons, continuous new sources of light, so many that even with this vast delay built into the system, the surface remains radiant. It is as though the sun is constantly filling a vessel with water that takes centuries to drain, and yet the vessel never empties. The brightness remains steady, the warmth continues. This detail, this quiet understanding that light moves slowly through the sun's depths, even as it moves quickly through empty space, offers a kind of meditation on patience itself. The universe is not in a hurry, creation is not rushed. The sun takes its time with its own light, shepherding each photon carefully, allowing it to experience the full density and temperature of its own interior, before finally releasing it to travel through the void. And in that slowness, in that careful attention to each infinitesimal journey, there is something deeply calming, a reminder that the most important things often take the longest to arrive. The moment that ancient photon finally emerges into the photosphere, that luminous, gossamer skin of the sun that we recognize as its visible surface, it has traveled not merely through space, but through nearly 8,000 years of its own existence. And there, in that threshold between the sun's hidden depths and the open cosmos, something remarkable happens. The photosphere is neither as simple nor as still as it might appear from our distant vantage point on Earth. If you could drift close enough to examine this delicate boundary in silence, you would discover that the sun's visible surface is alive with a restless, gentle motion. The photosphere is approximately 500 kilometers thick, a thin envelope of roiling gas where the temperature begins to cool from the inner furnace of millions of degrees. But thin though it is, this layer holds the sun's true visage. It is here that light is finally released into freedom, having clawed its way outward through the crushing interior for thousands upon thousands of years. What makes the photosphere so soothing to contemplate is the existence of something called granulation. Imagine, if you will, the surface of a slowly simmering pot of water, where the heat beneath creates gentle hexagonal cells of rising and falling fluid. The sun's photosphere exhibits a remarkably similar pattern, though on a scale almost impossible to fathom. These granules are vast convection cells, each one stretching roughly 1,000 kilometers across, a distance that would take a jet aircraft many hours to traverse. And yet within the context of the sun itself, they are fine, delicate textures, a kind of cosmic quilting that shifts and breathes with a slow, hypnotic rhythm. The origin of these granules is patient and inevitable. Deep within the convective zone, just beneath the photosphere, energy rises in the form of heated plasma. This superheated material drifts upward, driven by the relentless pressure of the sun's own weight pressing down from above. As the plasma reaches the photosphere, it cools and radiates its light away into space. Once it has surrendered its warmth, it becomes denser and begins to sink back downward, descending toward the depths from which it rose. And so the cycle continues, endless and gentle, like the breathing of a sleeping giant stretched across 109 times the diameter of our Earth. These rising columns of plasma appear as bright, radiant areas within each granule, while the spaces between them, the cooler material sinking back down, appear as thin, darker lines creating the network. To observe this granulation pattern through the most advanced telescopes is to witness something like living texture, an ever-changing mosaic where individual granules emerge, shift, and dissolve over the course of mere minutes. A single granule's entire lifetime is typically brief, rarely lasting longer than 10 to 20 minutes. And yet from that endless choreography of birth and dissolution emerges the stable, nourishing light that has illuminated life on Earth for billions of years. There is something profoundly comforting in understanding that even the most seemingly permanent features of our sky are in fact composed of constant, gentle change. The sun's photosphere is not a static stage, but rather an active canvas where energy and matter perform an intricate dance. The granulation pattern ripples and shifts, and if you could somehow remain aware while listening to this narration, if your mind could sustain that delicate balance between sleep and wakefulness, you might recognize in this image a kind of metaphor for the nature of constancy itself. What appears unchanging is actually alive with subtle motion. What seems permanent is composed of billions of ephemeral moments flowing together. Beneath the visible granules, there exist even finer structures that modern solar physics has only recently begun to map with clarity. There are smaller-scale convection patterns, supergranules, they are called, that are perhaps 30,000 kilometers in diameter and persist for considerably longer, sometimes for an entire day or more. These supergranules seem to organize the granulation patterns into a larger architecture, a hierarchy of circulation that brings order to what might otherwise appear chaotic. It is as though the sun possesses an invisible scaffolding upon which its visible surface is constructed. The photosphere is also where one begins to perceive the sun's magnetic field making its presence known. Though magnetism is invisible, its effects ripple across the sun's surface in ways that can be observed. The temperature variations you would detect across the photosphere, the slightly cooler and slightly warmer regions, are influenced by the movement of this vast magnetic force. The sun is not merely a ball of inert plasma, but rather a dynamic, magnetized body whose properties are woven into every photon of light it releases. What emerges from this contemplation of the photosphere is a sense of profound stability coupled with infinite, patient motion. The sun's visible skin is a place of constant creation and dissolution, where energy released from nuclear fusion deep within finally escapes into the void and begins its journey toward our world. Every moment, in the photosphere's granulation patterns, the same process unfolds. Heat rising, light radiating, cooler matter sinking, the cycle renewing itself millions of times over. Now, if you were to gaze at the sun through proper protective filters, you might notice something remarkable on its glowing face. Dark patches that seem to drift slowly across that brilliant sphere. These are sunspots, and they tell a story that astronomers have been quietly listening to for centuries. What many people don't realize is that these dark regions aren't actually dark at all. They're merely cooler than their surroundings, appearing in shadow only by comparison to the incandescent brilliance around them. A sunspot is still hotter than the surface of any forge on Earth, yet it reads as a blemish against the sun's radiant skin. The reason sunspots appear at all is deeply connected to something invisible but utterly powerful: the sun's magnetic field. Deep within that roiling, churning interior, electric currents flow and spiral in patterns we're still learning to fully understand. These currents generate magnetic fields of extraordinary strength, far more intense than anything we can create in our laboratories. Over time, these magnetic lines of force become twisted and tangled, like an invisible rope being wound tighter and tighter. Sometimes, in the turbulent dance of the sun's convection zone, these magnetic field lines push upward through the photosphere, breaking through to the surface. Where they emerge, they create a kind of magnetic knot, and that knot somehow suppresses the normal upwelling of heat that would otherwise rise from below. The result is a cooler patch on the sun's face, a sunspot. What makes sunspots especially fascinating is that they don't appear randomly scattered across the solar surface. Instead, they follow a rhythm, a cycle so precise that it's been measured and observed for more than 3 centuries. This is the solar cycle, and it unfolds over approximately 11 years. During the minimum phase of this cycle, there are few or even no sunspots visible on the sun. Then, as if the sun were stirring from a quiet sleep, dark patches begin to emerge. They don't appear at the sun's equator, but rather at higher latitudes, around 30 degrees north and south. As the cycle progresses, more and more sunspots form, and they gradually drift closer to the equator, tracing an invisible path as the years slip by. At the maximum of the cycle, when the sun is most active, there might be dozens of sunspots visible at any given moment, each one a temporary disruption in the sun's magnetic order. Perhaps the most intriguing aspect of this rhythm is that no one fully understands why it lasts exactly 11 years. There's something within the sun, some internal engine or pattern, that beats out this cosmic metronome with remarkable consistency. It's as if the sun has a hidden clock, one wound by the movement of plasma, the dance of magnetic fields, and forces we're still struggling to comprehend. Researchers have observed that this cycle might be regulated by what's called a dynamo effect, the way moving, electrically conducting fluid can generate and maintain magnetic fields. Deep within the sun's interior, the rotating plasma acts like an enormous electrical machine, and perhaps the time it takes for that machine to cycle through its phases naturally settles into this 11-year period. As the cycle reaches its maximum, the magnetic tangles become more and more pronounced. The sunspots cluster together, and from these regions emerge phenomena of breathtaking intensity. But for now, in this slow moment, let us simply rest with the knowledge that the sun's face changes through the years, that it's not a static, eternal sphere, but rather a dynamic, breathing organism. The sunspots are visible proof that beneath that golden radiance lies a realm of invisible forces, of magnetic poetry written in plasma and fire. They remind us that even something as steady and constant as our sun is never truly still. It pulses, it cycles, it renews itself according to rhythms that stretch across years and perhaps even deeper cycles we haven't yet discovered. The dark patches drifting across the sun's face are merely the most visible song of this much larger dance. From beneath that calm, rippling surface of the photosphere, that slow-breathing skin, there stirs something far more dramatic, though we perceive it from such vast distance that it seems almost gentle. The sun, in its patient way, occasionally gathers enormous stores of energy in the twisted corridors of its magnetic field, and then, without warning, releases them. These are the solar flares. Imagine the sun taking a long, deep breath and holding it, while invisible magnetic lines coil tighter and tighter around each other like serpents winding into knots. The pressure builds silently for hours, sometimes days, while atoms dance faster and faster in the sun's upper atmosphere. And then, in what seems like a moment, the magnetic field suddenly snaps. It is as though the sun has exhaled all at once. When this happens, light of all kinds floods outward. Visible light, ultraviolet radiation, X-rays, even radio waves. These flares can brighten a region of the sun by 1,000 times, or 10,000, yet from our vantage point, they remain invisible to the naked eye. We know them only through instruments, through sensors that listen to the sun's silent songs. A major flare, in its intense way, releases energy equivalent to billions of nuclear bombs detonating simultaneously. And yet the sun does this and simply continues its slow fusion, as if nothing remarkable has occurred at all. But the flares are not the end of the sun's exhalations. Alongside them, and sometimes in their wake, come the coronal mass ejections, or CMEs, as astronomers gently call them. These are something more vast and more profound, if you can imagine it. Where a flare is a sudden flash of radiation, a CME is the sun expelling enormous clouds of plasma, that is, superheated gas composed of electrons and protons, directly outward into space. Billions of tons of material, torn from the sun's outer atmosphere, the corona, ejected into the void in the space of mere minutes. Picture this: from the sun's surface, a bubble of magnetized gas rises and rises, following the invisible lines of magnetic force. As it climbs, it grows cooler, denser. The magnetic field holds it in place, but the pressure builds. And then, at some threshold we do not fully understand, this is where the solar mysteries still whisper their secrets, the field releases. The entire cloud of plasma erupts outward, traveling sometimes at speeds exceeding 3 million kilometers per hour. 3 million kilometers per hour. In some cases, these ejections can be observed taking place over the course of several hours, unfolding like the slow opening of a celestial flower, though the speeds themselves would make any earthly motion seem frozen in time. What makes these events feel almost dreamlike is the silence of them. In space, there is no sound. The sun could be performing these tremendous violent exhalations, these cosmic gestures of unimaginable power, and we would perceive nothing but light and magnetism. The collision of particles, the rush of plasma through the vacuum, the great invisible waves spreading outward, all of it silent as sleep itself. The sun breathes out its rage into a void that does not echo. These coronal mass ejections follow a pattern, or seem to. They occur more frequently during what is called the active phase of the solar cycle, those years when the 11-year rhythm brings the sun to peaks of tumultuous energy. During the quieter years, they are rarer. But even this is not entirely predictable. The sun keeps its own counsel about when it will next exhale. Astronomers can sometimes recognize the conditions that favor an eruption, can point to magnetic configurations that seem unstable, but the precise moment of release remains shrouded in the sun's ancient mathematics. And here is a quieting thought. These flares and ejections, dramatic though they seem on the sun's scales of magnitude, are part of its very nature. They do not harm the sun. They do not deplete it. They are as natural to it as breathing is to you, a gentle cycle of building and releasing, tension and rest, pressure and relief. The sun has been doing this for 5 billion years, and it will continue doing so for billions more. These eruptions are not signs of age or decay, but rather the constant work of a star maintaining itself, regulating itself through cycles of disturbance and calm. From the sun's corona, these exhalations stream outward. They are exhaled into the waiting darkness, and somewhere, very far away, on a small blue planet that orbits this patient breathing star, they will arrive. Far beyond the sun's shimmering surface, beyond the outer reaches of the corona's delicate halo, something invisible begins to happen. The sun does not simply radiate light and warmth and hold them close. Instead, it releases something else entirely, something that flows outward in all directions at once, like the gentlest tide imaginable, moving through the emptiness of space without sound or visible form. This is the solar wind, and it has been streaming away from the sun since the very moment our star was born, 5 billion years ago. The solar wind is born from the sun's outer atmosphere, the corona, where temperatures reach millions of degrees. At such tremendous heat, the sun's grip on its own particles begins to weaken. Atoms and electrons, ionized and energized, begin to escape. They pour outward in a constant, invisible flow, moving at speeds between 200 and 900 kilometers per second, depending on where the wind originates and how the sun's magnetic field shapes it. Think of it as the sun breathing out, slowly and eternally, releasing its own essence into the void. This wind moves so gently that you would never feel it on your skin, yet it carries with it a force that reshapes entire regions of space. It flows past Mercury and Venus, past our Earth, past Mars and the asteroid belt, and continues on toward the outer planets, gradually slowing as it travels but never truly stopping. The solar wind is so constant, so reliable, that it has a rhythm all its own. During quiet periods, it moves in a more or less steady stream. But when the sun grows restless, when a coronal mass ejection occurs, or a solar flare bursts across the surface, the wind intensifies, surging outward in waves that take a few days to reach us here on Earth. The particles that make up the solar wind are primarily protons and electrons, the building blocks of hydrogen plasma. As they drift outward from the sun, they carry with them the sun's magnetic field, twisted and tangled by the sun's rotation. Imagine the sun slowly spinning on its axis once every 27 days, twirling its own magnetic lines like threads being wound on an invisible spool. This rotation imparts a spiral structure to the solar wind itself, a vast, slow spiral that extends across billions of kilometers. Astronomers call this the Parker Spiral, named after Eugene Parker, who first predicted the solar wind's existence in 1958. It is one of the great discoveries of modern solar physics, yet it remains mostly invisible to our eyes. What does the solar wind do as it travels? It sweeps outward, carrying the sun's influence farther and farther into space. It fills what we call the heliosphere, the vast bubble of solar influence that extends well beyond Pluto, beyond the reach of most of our instruments, into a realm where the sun's dominance finally begins to fade and the interstellar medium begins to assert itself. The solar wind maintains this bubble, pushing back against the cosmic radiation and magnetic fields of the galaxy itself, creating a kind of protective sphere around our entire solar system. The pressure exerted by this wind is subtle but real. If we were somehow to sail a spacecraft with a solar sail, a thin reflective material that catches the photons and particles of the solar wind, we could use that pressure to propel ourselves across the solar system without burning any fuel. NASA and other space agencies have tested such sails, and they work. The solar wind, invisible and gentle though it may be, can actually move an object. It is one of nature's most elegant forces, a tide that has no water, no weight, no visible substance, yet carries momentum and energy across the void. As the solar wind travels outward, it interacts with everything in its path. It batters the tails of comets, pushing their dust and gas into those long, flowing tails that we see so beautifully during rare cometary visits. It carries particles and radiation that can affect the orbits of tiny dust grains floating in the solar system. It shapes the environment around every planet, every moon, every asteroid. In a very real sense, the solar wind is the medium through which the sun speaks to the rest of the solar system, a constant, gentle conversation carried out in particles and magnetic fields. The solar wind also varies with what we might call the sun's mood. During the solar minimum, when the sun's magnetic activity is at its lowest, The wind is more uniform and predictable. During the solar maximum, when sunspots are numerous and solar flares dance across the surface, the wind becomes turbulent and variable. This cycle happens roughly every 11 years, though the exact timing is not perfectly regular. It is as though the sun breathes in great, slow cycles, and the solar wind breathes with it, speeding and slowing and guiding the rhythms of space around us. The particles in the solar wind move so fast that they reach the inner planets in just a few days. A disturbance near the sun might reach Earth in 3 or 4 days, depending on its size and intensity. This is how we know, sometimes with a few hours' warning, that a strong solar wind event is coming our way. Scientists monitoring the sun watch for the initial flare or eruption, and then they wait, knowing that the consequences will arrive within days, riding invisible on the solar wind. Here is something remarkable to consider. The solar wind has been flowing outward for billions of years, a constant exhalation from our star, yet most of it escapes the solar system entirely. Very little of it is captured or destroyed. Most of it simply continues outward, spreading into the interstellar medium, eventually mixing with the vast ocean of space itself. Some of the particles that left the sun when your parents were born are still traveling outward now, carrying the sun's signature farther and farther from home. In this way, the sun writes itself across the galaxy, one particle at a time, in a story told in invisible ink that will never be fully read. The solar wind connects us to the sun in a way that is both profound and utterly ordinary. Every breath you take contains oxygen created in stellar furnaces. Every atom in your body was once part of a star. And right now, as you rest and listen, the solar wind flows past Earth, past you, carrying particles and energy that the sun released millions of years ago. It is a tide without water, a current without flow, yet it moves through space with patient purpose, shaping our solar system's architecture one particle at a time. And so that solar wind, that endless breath exhaled from the sun's corona, travels outward through the empty cold of space, carrying with it fragments of the star's own magnetic field, wisps of charged particles moving at speeds around 400 kilometers every second. For 8 minutes it has already journeyed toward us. For millions of miles more, it will continue its invisible journey, streaming past Mercury's scorched face, past Venus in her thick clouds, and eventually reaching our own blue world. But Earth is not defenseless against this cosmic tide. Wrapped around our planet, invisible yet present, is something extraordinary. A vast magnetic field generated deep within our turning molten core, and it extends outward into space like an enormous invisible embrace, like an atmosphere made purely of magnetism. When the solar wind arrives at this magnetic boundary, this invisible shield we call the magnetosphere, something remarkable begins to unfold. The charged particles carried on that wind do not simply crash into our atmosphere. Instead, they are caught, gently redirected, guided along the magnetic field lines that arch from the North Pole toward the South Pole and back again, tracing invisible pathways through the upper reaches of our sky. Some of these particles spiral downward along these magnetic corridors, descending toward the poles, drawn inexorably toward regions of concentrated magnetic force. And as they descend, traveling faster and faster through the thin upper atmosphere, something begins to glow. In the far north, above the Arctic Circle, and in the far south above Antarctica, the night sky sometimes awakens with color. Emerald greens and soft purples, pale pinks, and occasional deep reds bloom across the darkness in rippling sheets of light. This is the aurora, sometimes called in the north the Northern Lights, and in the south the Aurora Australis, the Southern Lights. And these are not distant phenomena, not something happening on some faraway star. These are born here, between the sun and our own home, an encounter written in light between two magnetic forces separated by 93 million miles. The mechanism is delicate and precise. As the solar particles collide with atoms of oxygen and nitrogen in our upper atmosphere, at altitudes between 100 and 300 kilometers above the surface, their energy is transferred. These atmospheric gases, suddenly struck by particles traveling at tremendous speed, become excited, their electrons jumping to higher energy states. And when these excited electrons fall back to their normal states, they release that excess energy as light. A single oxygen atom struck in this way releases a photon of green light, the color that most commonly paints the northern sky. Nitrogen, struck similarly, releases light that appears blue or red, depending on the energy involved, creating those deeper, rarer hues that sometimes dance at the edge of an aurora. Have you ever wondered why auroras are strongest at the poles and not at the equator? The answer rests in the geometry of our magnetic field itself. The field lines emerge from near the South Pole, arch outward into space, and curve back to enter near the North Pole. This creates what scientists call the auroral oval, a ring of activity circling each pole, roughly between 60 and 70 degrees of latitude. When solar activity is moderate, auroras remain confined to this oval, visible mainly to those living in the far north or far south. But when the solar wind strengthens, when a coronal mass ejection arrives with particular force, the auroral oval expands, pushing southward and northward, making auroras visible to populations at lower latitudes, sometimes as far south as the northern United States or even farther. The light show that results is not random or chaotic, though it may appear so to an observer standing beneath it. The particles follow predictable paths. The light appears in waves and curtains because the magnetic field itself has structure, and the particle streams follow the contours of that invisible architecture. Sometimes the aurora appears as a simple arc, a gentle band of light drawn across the sky. Other times, it explodes into what is called an auroral substorm, brilliant, rapid movements, dancing waves of color that seem to shimmy and shift with almost fluid grace. These events peak roughly every 10 minutes, expressing themselves in bursts of intensity that can light up the night so brightly that one can read by the aurora's gentle glow. Throughout human history, those living at high northern and southern latitudes have witnessed these displays with wonder and with meaning. Indigenous peoples watched them with reverence, wove them into story and spirituality, understood them as messages from realms beyond ordinary sight. Scientists, too, have found in them extraordinary beauty, not merely as aesthetic spectacle, but as visible proof of the connection between our star and our world, evidence of magnetic forces and invisible particles made luminous. What makes an aurora so profoundly calming to observe, perhaps, is that it represents a kind of cosmic dance witnessed directly, yet safely. The particles have been guided and gentled by our magnetosphere, transformed from potentially harmful radiation into light. The danger that might exist has been mediated by our planet's protective field. We stand beneath a light show born from the far side of the sun, and we are safe. The aurora glows above us, a reminder that we are held, cradled within the geometry of our world's own magnetic embrace, watched over by forces far older and vaster than ourselves, yet arranged in such a way that we are protected. And in the gentle rippling of that light, in the slow shifting of color across the polar night, there is something that speaks to rest itself, something that suggests that even in the vastness of space, even in the fierce churning at the sun's heart, even in the violent streams of particles crossing the void between worlds, there can be balance, there can be harmony, there can be moments of pure, serene beauty made manifest in light. And so, high above your sleeping world, there moves a dancer whose performance happens only rarely, and then only for the briefest moment. The moon, that quiet companion orbiting Earth, occasionally steps directly between you and the sun. When this happens, the sun's light does not disappear entirely at first. Instead, it begins to dim, as though someone were slowly turning down a vast cosmic lamp. The edge of the moon's shadow first touches the edge of the sun, and from certain places on Earth, watchers can see the sun begin to shrink, becoming a crescent of brilliance against the blue of the daytime sky. This is the beginning of what astronomers call a solar eclipse, though the term seems almost too clinical for something so quietly profound. For what is happening, in essence, is a celestial geometry so precise that the moon's disk, which is 400 times smaller than the sun, has learned to fit itself almost perfectly in front of that enormous ball of light. The moon orbits much closer to Earth than the sun does, and though the sun is incomparably larger, the distances involved in space work in the moon's favor, creating what we might call a cosmic accident of proportion. The moon's shadow rushes across the Earth's surface at tremendous speed, sometimes moving faster than 1,000 miles per hour. Yet to those standing in its path, the eclipse unfolds as if in slow motion. Consider what happens during those minutes before totality arrives. The light takes on a quality unlike any other hour of the day. The sun, as it shrinks into a crescent, begins to paint the sky with colors that seem borrowed from no earthly source. The quality of shadows changes. Objects beneath trees develop strange, flickering patterns, as though the forest itself has begun to breathe differently. The air, which has been touched and warmed by that 8-minute-old light, begins to cool slightly. Animals may grow confused, sensing the approach of what their instincts tell them should be night, yet the world has not transitioned into darkness gradually as it should. And then, if you are fortunate enough to be in the path of totality, the moon slides fully in front of the sun. The disk of the sun vanishes, and in that instant, something remarkable becomes visible: the solar corona. During all other moments of your life, the sun's brilliant surface, the photosphere, overwhelms the fainter light of the corona with its sheer intensity. But during totality, that fierce disk is blocked, and suddenly the corona reveals itself, a crown of wispy light streaming outward into space, like the breath of the star made visible. It is pale, ethereal, something your eyes have never truly perceived before, because the sun's everyday brilliance has always hidden it away. The temperatures during totality create their own strange magic. The ground temperature can drop by 10 degrees or more in just minutes. The sky darkens, but not to complete blackness. Instead, it becomes a color somewhere between twilight and night, as though Earth has slipped briefly into some realm that exists between day and sleep. Stars appear in the daytime sky. A cool wind might move across the landscape, as if the solar wind itself has somehow become visible and tangible. And yet this profound moment lasts only briefly. The maximum length of totality, when the moon's shadow completely covers the sun, can be at most 7 or 8 minutes, though most eclipses last only 2 or 3. The moment passes with an almost startling suddenness. The sun's edge emerges from behind the moon's disk. Light floods back across the landscape at tremendous speed. The color returns to normal. The temperatures begin rising again. The animals that fell silent return to their ordinary songs and movements, as though nothing remarkable had just occurred. What makes a solar eclipse possible is a question worth sitting with for a moment. The moon does not always pass directly in front of the sun, though it orbits the Earth faithfully every 27 days. The moon's orbit is tilted slightly relative to Earth's orbit around the sun. Most of the time, the moon passes either above or below the sun's position as seen from Earth. But a few times each year, the geometry aligns. The moon's orbit crosses the plane of Earth's path around the sun at points called the lunar nodes, and if the new moon occurs near one of these nodes, the shadow falls. The frequency of eclipses follows patterns that ancient astronomers discovered through patient observation. Eclipses occur in a cycle called the Saros, a period of approximately 18 years and 11 days. This means that if you experience a total solar eclipse on a given date, a similar eclipse will occur in the same geographic region again after that cycle completes. The patterns are so regular that modern astronomers can predict solar eclipses centuries in advance, calculating not only when they will occur, but also where on Earth's surface the moon's shadow will travel, and how long totality will last at each location along that narrow path. There is something deeply moving about the predictability of an eclipse, yet its relative rarity. For any given location on Earth's surface, a total solar eclipse is a rare event. You might wait decades, or perhaps an entire lifetime, to witness totality from your home. The eclipse path, that strip of Earth where the moon's shadow actually touches down, is typically only about 100 miles wide. It is a narrow corridor of shadow racing across the landscape at tremendous speed, and it touches any given place only briefly across centuries or millennia. This is why eclipse chasers have become something of a phenomenon, traveling across the world when forecasts predict the moon's shadow will pass through a region they can reach. What is remarkable too is that an eclipse is not primarily a solar event. The sun continues burning as it always does, unchanged and indifferent to the moon's motion. Rather, an eclipse is a story about perspectives, about geometry, about the precise arrangement of three bodies, the sun, the moon, and Earth, in a moment of alignment. The sun is doing nothing different. The moon is simply moving along its ordinary orbit. Earth is simply rotating and orbiting as always. Yet because of where these three bodies happen to be in relation to one another at a particular instant, the experience of those watching from Earth transforms completely. Light is briefly stolen. The familiar becomes strange. The eternal becomes temporary. And in the moments after totality ends, as the sun gradually returns to its full, blinding brightness, something quiet shifts in those who have watched. They have glimpsed the sun in a new way. They have seen its corona, that crown of mysterious light. They have stood in the moon's shadow. They have witnessed the orderly mechanics of the solar system expressing themselves in a ballet of moving objects and changing light. The experience carries with it a sense of calm witness, of having been present for something arranged by forces far grander than any individual life, yet made meaningful because of the consciousness present to experience it. And here, in this moment of understanding the sun's patient architecture, we might pause to consider something equally profound, yet so woven into the fabric of daily existence that we rarely notice its presence. The sunlight that reaches Earth, that same 8-minute-old photon now warming your skin, carries within it the power to orchestrate the entire rhythm of our world. It is not merely light, it is the grand conductor of seasons, the sculptor of oceans, the keeper of time for every living thing that has ever drawn breath upon this planet. Consider, if you will, the tilt of Earth's axis, that slight, gentle lean at about 23.5 degrees from vertical. It seems almost incidental, a minor geometric detail, and yet it is everything. As our planet traces its slow ellipse around the sun, this tilt means that different hemispheres receive the sun's rays at different angles throughout the year. In winter, your hemisphere tilts away, and the sunlight arrives more obliquely, spreading itself across a wider surface of atmosphere and ground, and so it warms less intensely. The days grow shorter. In summer, your hemisphere leans toward the sun, and those same photons arrive more directly, concentrating their energy, and the days stretch longer. It is a rhythm so old, so fundamental, that plants and animals have learned to read it like a language written in light and shadow. The ocean, too, obeys the sun's patient command. The heat that accumulates in tropical waters, stirred by sunlight into the upper layers of the sea, creates vast currents that wrap around the globe like slow-moving arteries. These currents carry warmth from the equator toward the poles, moderating the climate of continents, softening the harshness of regions that might otherwise be locked in eternal ice or scorched by relentless heat. The Gulf Stream, that river within the Atlantic, owes its existence to the sun's differential heating of Earth's surface. Without it, much of northern Europe would resemble the frozen territories of Canada at similar latitudes. The monsoons that bring rain to billions of people arise from the same principle. The sun heating land masses more quickly than oceans, creating pressure systems that drive winds and clouds across thousands of miles. Have you ever considered that the water you drink, or the breath you take, is shaped fundamentally by where the sun's rays struck the planet weeks or months or years before? And the green things, the plants that cover the land, that fill our forests and meadows and gardens, they are, in their essence, solar panels of incomparable sophistication. Through photosynthesis, a process that is itself still not entirely understood in all its elegant complexity, plants capture the energy of sunlight and transform it into the chemical bonds of sugar and cellulose. Every blade of grass, every towering oak, every grain of wheat that feeds human civilization is, quite literally, captured sunlight made solid. The speed and rhythm of this transformation responds to the angle and intensity and duration of sunlight. In spring, as the days lengthen and the sun climbs higher in the sky, plants awaken from dormancy, budding and unfolding as if following an instruction written in photons. In autumn, as the sun's arc lowers and the nights grow longer, they sense this shift and begin their slow preparations for winter, drawing nutrients back into roots, thickening their skins, darkening their leaves as chlorophyll is dismantled and recycled. The animals that feed on plants, and the animals that feed on those animals, are all, in turn, feeding on captured sunlight. The meat of a cow is sunlight transformed through grass into muscle. The fish in the ocean feeds on plankton that photosynthesize in the sunlit upper waters. The hawk that hunts the fish is, ultimately, consuming photons that fell on the sea weeks before. This is not metaphor, it is literal. Every calorie of energy that flows through the web of life on Earth originates as radiation from the sun's fusion-born core. When you eat, you are consuming ancient light. And then there is time itself, the day and night cycle that has shaped the evolution of life in ways we are still discovering. The circadian rhythms that govern your sleep and wakefulness, that regulate your body temperature and hormone production, that tell your cells when to be alert and when to rest. These are all entrained to the cycle of sunrise and sunset. Deep within your brain, in a tiny cluster of cells called the suprachiasmatic nucleus, there are neurons that respond directly to light. When blue wavelengths of sunlight strike your eyes in the morning, these cells fire, suppressing melatonin production and preparing your body for activity. As the sun sets and that blue light fades, melatonin rises again, gently encouraging your body towards sleep. This is not something you decide. It is something the sun has been teaching your ancestors, and through them you, for millions of years. Every creature on Earth, from bacteria to whales, carries within its being this ancient resonance with the sun's 24-hour pulse. There is something quietly profound in recognizing that you are not separate from this vast solar machinery. You are not a passive observer of the seasons and light and dark. You are woven into it. The calcium in your bones may have once been part of a star's core. The oxygen you breathe was forged in stellar furnaces. The energy that moves your muscles originates in the sun's heart, and the rhythms that govern your days and nights, that tell your body when to sleep and when to wake, are a direct inheritance from billions of years of evolution under a single, constant star. The sun shapes not only the world around you, but the world within you. It has written itself into your biology so deeply that you cannot separate yourself from it, nor would you want to. Even now, in the darkness of evening or the quiet of approaching night, the effects of today's sunlight are still unfolding within you, serotonin molecules drifting through your brain, melatonin beginning its gentle rise, your body temperature slowly descending in response to the sun's slow descent beyond the horizon. The sun continues its work even in its absence, even as it prepares you, through the chemistry of light and shadow, for the restful hours ahead. And yet, for all its grandeur, for all the patient fusion burning at its core, and all the light cascading outward in every direction, our sun occupies a rather humble place in the cosmos. If you were to step outside on a clear night, far from city lights, and cast your gaze upward at the dense spray of stars scattered across the darkness, you would be looking at something almost impossible to fully comprehend. There are more stars in the observable universe than there are grains of sand on every beach and desert on Earth combined. 2 septillion, or thereabouts, and our sun, this great glowing orb that dominates our entire sky, is one among them, simply one. Astronomers have given it a classification, a way of sorting the infinite variety into categories of temperature and size and luminosity. Our sun is what they call a G-type main sequence star, or more colloquially, a yellow dwarf. And within that quiet designation lies something both sobering and oddly comforting. Yellow dwarfs make up roughly 7% of all stars, billions upon billions of them scattered throughout the galaxy, burning with the same steady nuclear patience as our own sun. Not the most massive, not the brightest, not the most dramatic or explosive, simply middle, ordinary. The kind of star that, in the grand architecture of the universe, represents normalcy. Consider for a moment the stars that do not share this modest status. There are red giants, swollen and cool, having already exhausted the hydrogen in their cores and begun fusing the elements surrounding them. There are white dwarfs, the dense and dying remnants of stars that have shed their outer layers, cooling slowly over billions of years into an increasingly cold darkness. There are neutron stars, so impossibly compressed that a teaspoon of their material would weigh as much as a mountain. And then there are the blue supergiants, those rare and violent exceptions that burn with such fierce intensity that they exhaust their fuel in mere millions of years rather than tens of billions. Sirius, Rigel, Betelgeuse, names that seem to carry weight, significance, the celebrities of the stellar world. Yet it is precisely this ordinariness that grants our sun its stability, its continuity. The yellow dwarfs, you see, are the long-distance runners of the star world. They burn their fuel slowly and steadily, allowing them to maintain nearly unchanging conditions for billions of years. This consistency, this reliable glow, is what has permitted life to evolve and flourish on the small blue planet that orbits nearby. A more brilliant star, burning faster, would have consumed its hydrogen in a fraction of the time. A dimmer star would not have warmed the early Earth sufficiently for liquid water to gather. The sun is, in this sense, perfectly calibrated, not exceptional, but suited, matched to the world it illuminates. If you were to travel outward through the galaxy, leaving our solar system behind, you would encounter thousands of other yellow dwarf stars, some perhaps with their own planets, some harboring their own possibilities. The nearest of these, Proxima Centauri, is a red dwarf rather than a yellow one. But among the true yellow dwarfs, the nearest known is Tau Ceti, about 11.9 light-years away. Imagine that distance. Light from our sun takes 8 minutes and 20 seconds to reach Earth. Light from Tau Ceti takes nearly 12 years. And yet both stars are, astronomically speaking, neighbors, close enough to be considered part of the same galactic neighborhood. What is remarkable, though it may not seem so at first, is that astronomers have discovered that planets are extraordinarily common around these yellow dwarfs. Most stars, it appears, are accompanied by worlds. Some of those worlds may harbor conditions not entirely unlike those on Earth. Liquid water, moderate temperatures, a protective atmosphere, the possibility, remote as it remains, of life. and yet we know almost nothing about them. They remain dark and unnamed, invisible to the naked eye, distant beyond human comprehension. Our sun, in its ordinariness, may be one of countless suns supporting countless worlds. This perspective, when truly allowed to settle into consciousness, carries a kind of peaceful weight to it. There is a humility in recognizing that the great burning ball that has seemed, throughout all of human history, to be the center of everything is actually quite typical, unremarkable, one member of a vast community of stars. And yet there is also, paradoxically, something comforting in that same realization. Because if our sun is ordinary, then the conditions it provides are likely not unique. The physics that governs its burning is the same physics that governs billions of others. We are not the result of some extraordinary cosmic accident, but rather participants in a vast, unfolding pattern that plays itself out again and again across the galaxy. The Milky Way itself, that pale river of light stretching across the night sky, contains somewhere between 100 and 400 billion stars. The estimates vary, depending on the method of measurement, but the scale is consistent, incomprehensibly vast, and yet we can point to it, we can see it, we can know, with some certainty, that our sun is one small spark in that greater light, not more important than the rest, not less important either, simply part of a larger, more complete picture. As you rest here, in the darkness, you might reflect on this quiet truth. The same star that has warmed this planet for 4.5 billion years, that has driven the cycles of seasons and the blooming of life, that has inspired myths and worship and wonder in the human imagination, is simply one among multitudes, a yellow dwarf, patient, stable, unremarkable, and in that ordinariness there is a kind of permanence, a kind of promise. The sun will continue to burn as it has burned. The night sky will continue to scatter its light toward distant worlds we will never see, and the gentle patterns of existence will continue their slow and peaceful rhythm, sustained by the ordinary constancy of an ordinary star. And yet, for all the stable constancy we perceive in the sun's daily arc across our sky, there exists a slow, inevitable story written into its very core, a story that unfolds not in years or centuries, but in the deep time of billions. The sun, you see, is not eternal. It is aging, quietly, imperceptibly, and in perhaps 5 billion years, the brightest permanence in our sky will begin a transformation so profound that it will gently, irrevocably reshape everything that orbits near it. For now, the sun holds itself in a kind of equilibrium. The outward pressure of its nuclear furnace presses against the inward crush of its own tremendous gravity, and they balance one another in a slow dance of opposing forces. But that balance, though it may seem unchanging across the span of a human lifetime, is in fact slowly shifting. Deep within the sun's core, hydrogen, the simplest, lightest of all elements, is being fused into helium. With each passing moment, the core becomes slightly richer in helium and slightly poorer in hydrogen. It is a process so gradual that the sun's luminosity increases by only about 10% every billion years. Yet increase it does. As more and more helium accumulates in the core itself must become slightly denser, slightly hotter, to maintain that crucial equilibrium. The outward pressure from the nuclear reactions at the core must remain just strong enough to resist the inward pull of gravity, and so the sun brightens. Ever so slowly, ever so steadily, in perhaps another billion years, the sun will be about 30% brighter than it is today, a threshold that some scientists believe may render Earth's oceans unstable, may cook away the atmospheres of our neighboring worlds. Life as we know it may have already ebbed from this solar system by then, though none can say with certainty what the future holds. But the true transformation awaits further still, in that distant epoch when the sun's hydrogen fuel begins to genuinely run low. When the last wisps of hydrogen in the core are fused away, fusion will suddenly cease in that deep, pressurized heart. What follows is a cascade of change. The core, no longer sustained by outward nuclear pressure, will collapse inward, not catastrophically, but gradually, over a span of perhaps 100 million years. That collapse will compress the remaining helium so intensely that it will grow hot enough to ignite a new kind of fusion. Helium nuclei will begin to fuse into carbon and oxygen. The sun will have found a new fuel source, a new equilibrium. But this new balance is different. The helium-burning core produces energy far more efficiently than the hydrogen-burning core did. The sun's outer layers, suddenly receiving more energy from below, will expand enormously, dramatically. The sun's radius will grow to perhaps 50 or 100 times what it is today, and as it expands, its surface will cool slightly, shifting from its current yellow-white toward a deeper, more orange hue. The sun will become a red giant. Imagine that transformation from some future vantage point. The sun would still rise and set as it does now, but it would fill perhaps a quarter of the entire sky, or more. Its red light would wash across a transformed solar system, painting everything in shades of ember and rust. Mercury would already be long gone, consumed into the sun's outer layers millennia earlier. Venus, so close to the sun now, would be enveloped in those expanding atmospheres, its rocky surface scoured away atom by atom, and Earth itself would find itself approaching the very edge of the sun's extended photosphere, threading what scientists call the habitable zone as it shrinks inward, a brief, precarious dance before the end. What happens to Earth in that moment remains subject to gentle speculation. Some models suggest our planet would be enveloped whole, its minerals mixing into the sun's outer layers. Others propose that Earth might survive, orbiting within the sun's sparse outer corona, though as a scorched, airless ember, a ghost of the world we know. The Moon, if it survives at the same distance it orbits now, would see that immense red sun rising to fill the sky above a dead Earth, and then slowly setting again, in a rhythm that would no longer be the rhythm of day and night, but the rhythm of cosmic death. The solar system would be transformed utterly. Jupiter and Saturn, so distant now, would become the inner planets of this new configuration. They might survive, though their atmospheres would be stripped away by the solar wind's fierce intensification. The outer reaches of the system would grow warmer, perhaps nurturing strange forms of existence in ways we cannot yet imagine. The asteroid belt would be scattered, some fragments falling inward to the sun, others flung outward into the darkness. This red giant phase would not last forever. It would persist for perhaps 1 billion years, a mere breath in cosmic time, before the sun would shed its outer layers entirely. The ejected material would form what astronomers call a planetary nebula, a vast, expanding shell of glowing gas illuminated by the sun's exposed core at its center. That core would cool over millions of years, becoming denser and denser, shrinking down to the size of the Earth itself, though possessing the mass of the entire star. It would become a white dwarf, a stellar ember, gradually radiating away its remaining heat into the void over timescales so vast that a white dwarf might take longer to cool completely than the universe has yet existed. A white dwarf at the center, perhaps the size of a marble yet weighing as much as the sun does now. Some handful of surviving planets, if any, orbiting in the darkness at vast distances, a remnant, a memory. The sun would be ancient, invisible to any eye that did not know precisely where to look. Yet from what distance might some consciousness, some distant future intelligence perceive the sun as it cools in eternal silence? The beautiful thing about this story, and perhaps the most soothing aspect of it, is that it is both distant and inevitable. Nothing can be done to hasten or prevent it. The sun will age as all things must age. The solar system will transform. Life on Earth, in its current form, will almost certainly not survive to witness these changes. And yet the story is already written, encoded in every photon that leaves the sun's surface, in every grain of hydrogen that fuses into helium in the deep core. The future is patient, the sun is patient, and in that patience there is a kind of peace. And so we drift back, through all those billions of years, through the swirling corona and the patient photosphere, through those hidden zones where light still journeys, back to the simplest, most ancient moment. The moment when warmth touches skin, close enough now to feel it, that gentle pressure of photons, those particles of light born so long ago, traveling across the vast emptiness, arriving still at this very instant on the surface of your body, 8 minutes and 20 seconds after they departed the sun's face. 8 minutes and 20 seconds to cross 193 million kilometers of silence. And in that time, you have not moved so very far. You remain here, breathing slowly, held in the slow rotation of a planet that turns, always, toward that distant, steady flame. There is something profoundly quiet about sunlight, when you consider what it truly is. Not a thing that burns alone in darkness, but a presence that has been arriving, without rest or complaint, for longer than any civilization has kept count. The sun has warmed skin. The sun has ripened fruit. The sun has turned the oceans, curved the spirals of galaxies in the fathoms of our sight, and made possible every breath of every creature that has ever lived, not through violence, through patience, through the quiet grammar of light. In its current form, the sun has perhaps 5 billion years remaining, 5 billion more years of burning. That is a difficult number to hold in the mind. It is longer than all of human history, longer than the existence of dinosaurs, longer than the formation of the continents as we know them now. And yet in the life of the cosmos, in the vast wheeling of billions of stars, it is merely ordinary. The sun is not a cosmic exception. It is not rare or special in the order of galaxies. It is one yellow dwarf among countless others, steady and modest, asking nothing of the universe except space to exist. And that is perhaps the deepest rest we might find in considering it. The knowledge that our sun is not alone in its constancy, that steadiness itself is the ordinary way of stars. What a thought to carry into sleep. The sun, at this very moment, continues its work. It does not sleep. It does not tire. In the depths of its core, gravity still presses, fusion still whispers, and the slow alchemy of hydrogen becoming helium continues uninterrupted, as it has for so many billions of years, as it will continue for so many more. The sun does not know that you are here, listening, thinking of its light on your skin. It does not need to know. It simply endures, and by enduring, it gives. That is the full measure of its relationship with you, with every living thing on this small turning world. The solar wind continues to stream outward, even now, pushing gently against the magnetic field that holds you safe. The auroras dance, though you cannot see them from here, at these latitudes where sleep is coming. The photosphere crackles with magnetic whispers. Somewhere in the darkness above, the stars themselves are far away, and the sun, among them, is closer than any other, and yet distant still. And all of this happens in silence. All of this happens without urgency. All of this happens while you lie here, breath by breath, your own small solar system turning in the dark. It is calming to remember that you are made of the sun's light, gathered into form. The calcium in your bones, the iron in your blood, the oxygen in every cell. These elements were forged not in the sun itself, but in ancient stars like it, in the tremendous explosions that seeded the cosmos with the possibility of life. You are made of starlight, in the most literal sense, and that light continues to arrive, particle by particle, warming you, sustaining you, asking nothing in return. The sun does not demand gratitude. It does not keep score. It simply gives what it is. Energy, constancy, the quiet heat of a star that has learned, over billions of years, to burn steadily enough that life itself could emerge and flourish. In millions of years, perhaps in 10 or 50 million years, other creatures will feel this same sunlight on their skin, though they will be so different from you that you would never recognize them as kin. And millions of years after that, others still. The sun will continue. It will continue long after everything you know has transformed into something unimaginable. And that too is restful. That is the peace that comes from understanding that you are part of something much larger, much older, much more patient than yourself. The sun asks only that you receive its gift, that you feel its warmth, that you let it touch you without resistance. That is all it has ever asked of anything, to shine and to be received. In this moment, as your thoughts grow slower and softer, as the edges between waking and sleep begin to blur, you are receiving. You are allowing the sun to touch you, not just through the light that arrives in brightness, but through the deeper warmth that has sustained every moment of your existence, every breath, every heartbeat, every thought. The sun is older than your worry. It is simpler than your doubt. It is here, steady and true, now and always. Let yourself drift now, the way the solar wind drifts outward through the cosmic silence. The sun will continue while you sleep. It will be there when you wake. It has been there all along, in the deepest constancy, the most patient presence. And you, warmed by light that travels